I'm Khaled from Core Intelligence, and we are a startup based in Bonn, Germany, specialized in software security testing. And yeah, so we have been working for many years now with automotive companies, including Continental, ZF, and VW. And today I am glad to be here to talk to you and discuss how can we test AUTOSAR applications for security issues in a software in the loop manner, and also discuss the main technology that we build in order to achieve that, which is our AUTOSAR simulator, and discuss how this enables us to sort of get into or unlock the potential to use superior testing methods like white box fuzz testing. Yeah, so in today's session, these are the points that we'd like to address, discuss the main challenges and the importance of testing AUTOSAR applications, and as I mentioned, so how white box fuzz testing can help finding more bugs and securing your software, and then discussing the how the simulator can enable you in order to apply fuzz testing at the system level. And of course, we will show a live demo so that you can see it in action, how you would be able to leverage this technology, and at the end, a Q&A session to discuss any questions that you might have. So, modern cars, there are an increasingly more software running on modern cars. So modern cars are, so the amount of software that we have on modern vehicles keeps increasing rapidly. And with that also increase the security risks. So, so now we started to see more often such headlines for like recalls and safety issues that are caused by software bugs. And of course, the goal here is not to single out any company. Here is another study, actually, a very interesting study that I recommend everyone to read here, where the security researcher looked into 19 automotive companies, and this includes all the major players from Asia, Europe, and the USA. And the results were really significant. So there have been severe security vulnerabilities found in these vehicles that enabled attackers, that would enable an attacker to go from full control over the car to even access the internal systems of these automotive companies, so and get even access to their source and internal development workflows. And so if we look at the trend here, that and according to one estimate from McKinsey, is that by 2030, 95% of the cars will be connected. This clearly demonstrates that security or software security for the automotive industry is a must. It's not a nice to have, it's a must. And on the good side, so the automotive industry seems to be one of the leading industries into taking security seriously, and having also requirements for thorough security testings. And as we discussed, so modern cars or cars that have evolved from being a completely or a purely mechanical machines to now being a software on the wheel devices. So at any modern car, you would have over 100 ECUs, which is electronic control units, which we can think of as small computers that does a certain task, like transmission control, anti-lock, infotainment, vehicle-to-vehicle communication. And these ECUs are connected to each other. This means that now we can think of a car as a network of these ECUs. And not only that, but the car itself is part of a bigger network. So to do things like over-the-air updates or autonomous driving. So, and this level of connectivity actually significantly also increased the attack surface. So it also increased the points where an attacker or a malicious player would be able to hack into the car. And yeah, so this is illustrates the fact that security is a must here, and the fact that we have now more and more software running on the car and different running on different chips actually triggered the need for standardization, so that we can, so suppliers and manufacturers can sort of have reuse the components or the application that they write. So this is similar to what we have in what we had in the early days of PCs, where just if you need to write to have some software for a different CPU or a different chip, you would need to rewrite everything from scratch. But then we had operating systems that abstracts away all the low-level hardware specifics, and it's actually based on as a result of this this fact, the need for standardization. This is where AUTOSAR is born, and yeah, so I don't need to go into details here for this audience, but mainly it's it's a standardization of how automotive software should be built, and it also, it's known here, it has two variants. So we have the classic platform, which is the first one that started, that was released 2005, and the adaptive one, which was released in 2017. And so currently, the main project that we work with are classic AUTOSAR, since it's older and it's more relevant still. This is would be the focus of today's webinar. And just a very brief overview, I guess this is also known to the audience here, but to have a look here to make it clear how the simulator, our simulator, fits in this picture. So for a classic AUTOSAR, so we mainly have three layers. You have the application layer, which is software or which is hardware independent. And then you have the basic software layer, which is hardware oriented, and this is, or hardware dependent, and this is the layer that offers all the services that are needed by the application layer. And these two are connected by the runtime environment. And so we will revisit this diagram when we talk about the simulator. And well, obviously these systems are becoming increasingly complex. As I mentioned, it's becoming also increasingly important to test for security issues. And also, as you know, so testing can be done at different levels. So you can do from unit testing to system level testing. So while the unit testing is important to identify to test the individual units in isolation, system testing is actually system level testing is crucial, because this enables us to test the end-to-end functionality, targeting the same interfaces. For example, in this case, like for example, CAN on Ethernet, are the same interfaces that an attacker might have access to. So the focus on this webinar is to show how can we do system level fuzzing or system level testing in completely in software. And if we have a look at the current approaches to do this to do system level testing, it's mainly done in a hardware in the loop setting, meaning that we actually need to run the system on the actual hardware, on the target hardware, and we need to actually have the hardware setup that's needed to run the system. And yeah, this has, of course, several challenges. Well, first, it requires, yeah, specialized hardware setup. So if you are working on an infotainment system, you might have to have a display there and all the different components that are needed to actually run the system. And this can be, yeah, can be rather costly and would limit your testing efforts. And of course, this effort in creating the setup makes it difficult to run these tests in parallel. So if we do unit tests or we do testing at the unit level and we don't have a more efficient test, we can just let these tests run in parallel. And doing this in a software manner, in a software in the loop manner is pretty easy. You can just spawn multiple instances of the test or running different tests on different CPUs. But if you need to have the hardware in the loop, you need to actually replicate this setup, which can be quite time consuming. And usually, when we talk about security testing, the way system level testing is done in a black box manner. And as we will see in a moment, if we do this in the software, this would enable us to access or to leverage superior testing methods that would enable us to have higher code coverage and find more bugs. So the main message here is that if we can manage then to have this level of testing in a software in the loop manner, we will be able to test the whole AUTOSAR application for bug without hardware. So we'll be able to actually address these limitations. So, but just want to make clear here, hardware in the loop is still necessary, is still needed. But if we can do majority of our tests in a software in the loop manner, this would simplify a lot of our testing setup. And this is actually the main motivation that we started developing the AUTOSAR simulator. And just to start with what we wanted to achieve with that. And it's actually, as we mentioned, we want to be able to test AUTOSAR application, complete AUTOSAR application at the system level, completely in the software in the loop manner. And so what this would give us mainly three benefits. So to address the issues that we discussed earlier. So it will enable us to uncover more bugs and avoid them being exploited. And the main idea or the main reason why this is the case is that this would enable us to, using the simulator, to apply white box fuzz testing. And we'll come to white box fuzz testing in a bit, which actually leverage all the insights from your source code to maximize code coverage and to find bugs more effectively. So this way we will find more bugs and prevent them to still be there in a software that you release in the car. And then with this manner, you would be able to then do your security testing much faster. And then and this is the reason why is that you will be able to run your complete tests in the software and even do this continuously, because now we have no dependence on the hardware, so we can even integrate these kind of tests in your continuous integration pipeline so that you can test your application with each code change. So this would give you a very fast feedback cycles or of any issues that might code by a code change. And these feedback cycles, as we know as developers, are key to quickly fix those issues. And yeah, by reducing the dependencies on the hardware, we will be able to reduce costs and optimize them by so not having to use this hardware for in our testing. And so one thing that you mentioned here is this white box fuzz testing, and we sort of just said that it's a superior method to find bugs and security vulnerabilities. But why is the case? So before having a look at white box fuzz testing, just want to emphasize that white box fuzz testing currently sort of is the best method to find bugs or security issues, or especially if we talk about memory unsafe languages like C or C++, memory corruption bugs in software. And for example, so big players like Google and Microsoft, they find most of their bugs with fuzz testing. So here's a few statements from them, and we know this also from our. So we have been collaborating with Google for years now, in their OS Fuzz platform, which is a platform to fuzz or to test open source applications, and to Core Intelligence provide their the fuzzing engines for Java and JavaScript. So just to illustrate that its fuzz testing is so effective that these companies heavily rely on it. So, but what is fuzz testing? And so you can think of it as at a very high level, it's actually very simple to understand what it does. So you have a system under test, which is actually your system that you want to test, and you have a fuzzer, and this fuzzer just throws some random input, some invalid random inputs into the application, and checking if there's any chance of having any input that actually causes this application to crash. So you can think of it as not a very smart person here trying to just randomly pressing your keyboard, just hoping to crash your system. And imagine now, instead of this not very smart, sophisticated monkey, you have an intelligent person who can make sense of what your computer is doing or how it's reacting to these keystrokes, and then based on that, trying to intelligently come up with good test cases, with to know what to press next, basically. And this is exactly how we can do it better. So this is exactly what now white box fuzz testing, and it's sort of one of the main technologies that we leverage and develop as Core Intelligence. And so the idea here is that you would leverage the detailed insight that we have from the source code. So for white box fuzz testing, we would need the source code. And as someone who is developing AUTOSAR application, you do have the source code for your application. And so using these insights from the code, then white box fuzz testing will be able to continuously generate test cases, smartly mutate these test cases to maximize code coverage and uncover more bugs than what you would get for black box testing. And as we mentioned in the beginning, so automotive industries is one of the leading industries where fuzz testing is required by ISO 21444. And so this is obviously not a deep dive session into fuzz testing. If there's interest, a question, we can dig deeper, but also feel free to have a look at our white paper of how what role fuzz testing plays, and also have a look at our other webinar where discuss or explain fuzz testing at a deeper level. Now why I'm telling this. So we said about fuzz testing. We have fuzz testing, which is ineffective, but it needs to run on so the most suitable environment for this to run, which would be an x86, or more specifically in the Linux x86 environment. But obviously, the AUTOSAR applications are not designed to run in this environment. So we have here, especially if we look at these lower layers here that are very hardware dependent, so they cannot run on the target architecture on which we would like to apply fuzz testing. And that's why we started developing our simulator. And the simulator actually replaces all these layers that are marked here. These would be then are replaced by the simulator. So we talk about the complex device drivers. We're talking about the IMCAL layers, and also part of the basically the OS. So this is then replaced by the simulator. And what this enables you to do is to actually run the other code, the one that's more or less software or hardware independent, to run it unchanged on top of the simulator. And what you get at the end is an application that you can run on a Linux x86 machine. And this is the environment that offers the best setup for white box fast testing. And you will see this in a demo shortly. And so this is the layers that are replaced by the simulator. So let's have a look at how does the simulator look like. And as I mentioned, so the goal here is that we replace the lower layers by sort of a Linux implementation, Linux-based implementation that enables your software under test to run on top of the simulator. And so that the simulator is also optimized for the also to be as lightweight as possible and to enable running white box fast test. So what you see here is that it offers an API to access the different functionalities. It does implement according to the AUTOSAR specifications the main drivers and interfaces that are needed there. For example, CAN, SPI, and ADC, for example. And at the bottom, you see the main components beside these interfaces, and this includes our own scheduler, just to be able to, so that you can actually schedule tasks and alarms that will be then run by the simulator or scheduled by the simulator. So, and then there it's obviously understand, for example, basic and extended tasks, and so this is then the part that would replace the OS. Then also we have the mutator, which is the way we generate test cases. Because as I mentioned again, so we want to test the AUTOSAR application at the system level. So that's why we target actually the known interfaces. So for example, the simulator would then be able to send CAN message to the software under test. And in order for this to be effective, the simulator needs to be aware of how a CAN message is structured. So for example, we have a CAN ID, and then comes the STU. So we know how the inputs that are expected by these interfaces, how should it be structured? Sorry. And the mutator is the smart person that can know how to change the next keystroke to press in order to maximize code coverage. And we have what we call the time machine. So one important thing with testing or with fast testing, because we actually iteratively executing or running the software with and sending some inputs, we need to guarantee that after each iteration, we reset the system state to its original state. So a time machine is the component that enables you to take a snapshot of your running system and then restore it before each puzzling iteration. And so this is, I hope, and yeah, one important thing. So this is the simulator, and then you have your software under test. So what you would then need to do in order to be able to use the simulator is writing some glue code. So what we call here as an adapter. As an adapter is nothing more than it's a piece of code that makes your software under test. So instead of actually calling the actual, for example, mcal layer or an actual function in the mcal layer, you would then code a corresponding function or from the simulator API. We'll see an example how this looks like. So this is at a high level how the simulator is structured. This is how you would then make your application talk to it. And now, and this is also explains which layers we replaced from the Classic AUTOSAR stack. And now I would like to show this in action in the live demo. But I have here. So imagine now, now I have, I don't know, an infotainment system that I want to test with the simulator or at the system level. And yeah, so here I have all the source code that I need to actually have a running system. So here in the core directory, you would see, yeah, the AUTOSAR code. So you see the communication, you see the diagnostics, see um, the code, the AUTOSAR code that needs to be run. So this is mostly the basic software layer. And so it's a Hello World example. It's a simple AUTOSAR application that makes some LED blink, and then it mainly communicate with the CAN interface. So you see here in the config file, you see have some configuration. So it's a generated code based on your configuration, and then we have here the source code. This is the sorry. This is the application layout software that you would write. Well, as you see in this case, we don't have too many files, so it's a rather a small code base that we're using here for demo purposes. But obviously, the scale of AUTOSAR application that we normally test with our customer are significantly higher than that. So we're talking about hundreds of thousands of lines of code, or even over millions of lines of code. But this is a small, sort of a well-contained small project that we will use here in the demo. And now, so I have my so I have my own code. I have generated code, and here in this directory, I have then my fuzzing setup. And so we built the simulator in a way that you can include your application as a library, basically. So here you see the AUTOSAR simulator as part of this fuzzing setup. And here we see the adapter, which is the piece of code that I needed to write to make my application here run with the simulator. We'll have a look at it a little bit later. And then we have here the fuzz test. So this is the actual test that the simulator would run. So as you see here, in the beginning, we will have, and so these namespaces are provided by the simulator. So in the beginning, in the test phase, I would just tell the simulator, so what are the valid CAN IDs that this software needs, how long you would need to run the OS. We do some initialization. We let the OS first run for 5 seconds just to make sure everything is initialized. And then here, if you remember this time machine, so we take actually then a snapshot of the current system state after we finish initialization, so that, and this is, so if you have used fuzz testing before, you need that, that you need to write a test that actually a fuzz test that the fuzzing engine executes in iteratively, and this is the whole fuzz test. So this will then be run iteratively, and in each iteration. So this is what we see as an AUTOSAR document. This represents the inputs for all interfaces like CAN, SPI that we mutate. Then all what you need to do is say, now please run the simulator with this fuzzer generated input. For example, sending some CAN messages and stuff like that. So this is the whole fuzz test that you would need to do. Now, with this setup, I can run this fuzz test that actually sends, for example, in this case, CAN messages to the system under test completely in software. So what this would enable me to do is just run this test as I would do with any normal test or with any unit level fuzz test. So here I can say CI fuzz, run this AUTOSAR fuzz test here. And now here I'm starting from a clean state. So we start from zero knowledge about this application. And now and CI fuzz is our command line tool or one of our products, which is a command line tool that it helps you to automate a lot of fuzzing jobs. Now, I can say go and run this fast test. So what you see here is at first the fast test will be built, and this means we build the whole code base, like the the application software, the basic software, so everything that needs to run, and then we start sending or inputs to the application. So here you see that this is one of the main numbers. You see that the code coverage, this is the branches that now we are visiting. So it keeps increasing over time, meaning that now we or CI files then automatically generate test cases that actually maximize code coverage. So here you see the code coverage, or more precisely the branch coverage. And here you see how many inputs we were able to generate in total, in a sense. So now in this small setup, so we are generating now 9,000 inputs. So we have been letting it run for a few seconds, and now we are seeing that we have more code coverage. And so now we see, oh, we triggered an issue. So now we have a global buffer overflow in this function. And just remember, we are fuzzing this software at the system level. We were just sending, for example, CAN messages and mutating everything. One of the main advantages of doing this white box fuzz testing, even at that level, is that for each finding, so actually we said we leverage the insights from the source code, so we know exactly where each bug happens. So now I say here's a global buffer overflow in this function that's happened at this exact location. So I can then even click here and go to exactly this mem copy that caused this problem. And this is a bug that I just here injected in this demo example just for demo purposes, and it took the fuzzer less than a minute to actually trigger it. So in this case, if these conditions are met, I would write 8 bytes to a 5-character buffer, causing a buffer overflow. And yeah, so what you also get is you can even observe this this finding more. And what you can also get is you get, and sorry if it's with that size not that readable, but what you get is you see so the exact stack trace, so the exact sequence of function calls that actually triggered this bug. So we started from the RTE here, from this function to that one here, and we triggered the bug. And now, obviously, this is not something I would show here, but you can also easily start a debugging session, for example, to understand the root cause. But with this stack trace and with this exact input, it becomes much easier to make sense or identify the root cause of what's happening here. So now if I now see that I need to allocate enough buffer here, I can then fix it, and then let me just clean my terminal and then start the fuzzer again. And now we will see that the fuzzer or that CI fuzz will not crash. So this is first, I can very quickly verify that with this fix, I was actually able to fix this bug, because this bug will not be reported now. Now we see we from the latest state that we ended up in. Now we continue to do more, to test more test cases to improve code coverage. And as I mentioned, so this is here. It's important to keep an eye on this number, because this should with the time keeps increasing. So each time we discover a new path or a new branch in your application, this numbers gets increased. So and the fact that it's keep increasing represent the fact that now we are still able to find new ways or new code to trigger in your application, new inputs that actually triggers new code. And this is an important criteria for such system, because at the end of the day, you want to know, okay, now I let the fuzzer run, or I tested my application. So how much code coverage do I have? Where was I able to reach 1%, 2%, 20%? So what's the code coverage? And this is one of the advantages of white box fuzz testing, is at the end, you can all the time get a coverage report, like a detailed report of or telling which lines of code you have yet to test. So if I stop it here right now, I can also then use CI fuzz coverage to ask CI fuzz, okay, now for this test that I've been fuzzing now for a few minutes, could you generate a coverage report? So could you tell me how much code I was able to cover? And so you see how the code is being built again, and this is the fact that for source-based coverage reporting, we need to build the code in a in a special manner as well. And yeah, so when the build is run, so we would then let this test actually run with the inputs that we already generated, so that we can get a coverage report. So in this case, so you see we get the report, and this is the final, so the aggregated number. So we have 37% line coverage, 40 so function coverage, 40% line coverage, and 31% branch coverage. Admittedly, this is low coverage number, so you should aim for larger coverage KPIs, and the sort of the usual metrics that we work with our customers, that we need to reach 80% line coverage or 80% function coverage. But keep in mind, I just let this run from scratch only for a few minutes. So usually you need to let it run a little bit longer to reach your KPI. And one of the really nice thing about this is that since now this is all done in software, and LCAP, for example, the one that the format that we generate is readily understood by IDE. So for example, if you have this report that we generated here, at least in VS Code, I can click here to see the lines of code that I was able to cover in my IDE. So now so this is an extension that you would need to install for VS Code. And now I see, okay, in my test, I will be able to cover these lines are green, which is nice. If we then maybe go to have a look at some other file, you would see, I don't know, here, for example, you see in this function, we cover something in the beginning, but there is here this block of code. It's not yet visited by the fuzzer. So we may need to let it run for a bit longer. So these details inside are usually very helpful for developers, or for you to know which portions of the application you test. And so one thing that I just wanted to show, because we mentioned these adapters, maybe one last thing, and this is the piece of code that actually glues the AUTOSAR, the system under test code, with the simulator. So if we have a look at one of these adapters, I just need coverage here, ADC, for example. So we offer this wrapper macro that you can use. And for example, if in this case, like you have ADC start group conversion, and this is an API from IMCAL. And so with this wrapper function and the way we support with it in our build system, so this would result in this function being sort of replaced or wrapped in the original application or software under test, so that when your software tries to call this one, so this call, instead of going to the IMCAL layer, it would actually go to this function and calls the corresponding API from the simulator. So this is just to show at a high level how this looks like. And these are sort of the main things that I wanted to show in the demo, just to illustrate the fact that with this, you can run or test the whole AUTOSAR application at the system level completely in software. And from the outside, it would appear as a normal or a standard unit test. And so this is the main things that, as I mentioned, I wanted to show in the demo, and just the main takeaways. So so I hope I was able to convince you that testing AUTOSAR applications for security issues is actually a must for the automotive industry, and you can, if you manage to do this in a software in the loop manner, you can unlock superior testing methods like white box fuzz testing. And it's for that goal why we built our AUTOSAR simulator to be as lightweight as possible and enable you to do this software in the loop testing and white box fuzz testing. And as I mentioned, with the simulator, you would be able to do this testing completely in software, so without hardware, and uncover more bugs and vulnerabilities due to the fact that you would have access to superior testing method like white box fuzz testing. And with that, I come to the end of my talk or webinar, and would be happy to take any questions you might have.